Robots are everywhere. Factory floors, hospital corridors, your living room vacuum. But what actually makes something a robot? And how do you build one? This series will take you from zero to building an autonomous robot that can navigate, avoid obstacles, and follow lines. Let's start with the fundamentals. A robot is a machine that can sense its environment, process that information, and act on it. 3 parts: sense, think, act. Sensors gather information, distance, light, temperature, touch. The processor, the brain, interprets that data and makes decisions. Actuators carry out actions, motors spin, arms move, lights blink. A remote-controlled car isn't a robot, it doesn't make decisions. A Roomba it senses walls, decides to turn, and acts by changing direction. The key is autonomy. The machine decides, not you. The think part needs a brain. For small robots, that's a microcontroller, a tiny computer on a single chip. A microcontroller has a processor, memory, and input-output pins, all on one chip. It's not powerful like your laptop, but it's perfect for reading sensors and controlling motors in real time. Why not just use a Raspberry Pi? You can, but microcontrollers are simpler, cheaper, and better at precise timing. For basic robotics, they're the right tool. Arduino isn't just a board, it's an ecosystem. Hardware, software, and a massive community. The Arduino Uno is the classic starter board, 14 digital pins for on-off signals, 6 analog pins for variable readings. Enough power to control motors, read sensors, and run your robot's logic. The Arduino IDE is where you write code. It's simplified C++, beginner-friendly but real programming. Every Arduino program has 2 functions. Setup runs once when the board powers on, use it for initialization. Loop runs forever after that, this is your main program. The workflow is different from regular programming. You write code on your computer, but it runs on the board. Write your code, hit verify to check for errors, then upload to send it to the board. The code transfers over USB and starts running immediately. Unplug the USB, the code stays. It's burned into flash memory. This is embedded programming. No operating system, no files, no network. Just your code running directly on hardware over and over forever. Your first program will blink an LED. It sounds trivial, but it proves everything works. The ID, the USB connection, the board, your code. That blinking light is your hello world. Robotics isn't just about building robots. It's about understanding how physical systems work with software. You'll learn to think in terms of signals, timing, and physical constraints. Software bugs become visible. If your code is wrong, the motor spins the wrong way. The feedback is immediate and tangible. These skills transfer everywhere: IoT devices, drones, manufacturing, medical devices, automotive systems. The fundamentals don't change. By the end of this series, you'll understand how to build an autonomous mobile robot. 2 wheels, sensors for distance and line detection, and a brain that makes decisions. We'll cover motors for movement, sensors for perception, and control algorithms for intelligent behavior. Each piece builds on the last. To recap part 1, a robot senses, thinks, and acts autonomously. The microcontroller is its brain, a tiny computer on a chip. Arduino provides the ecosystem, boards, IDE, and community. The workflow is write, compile, upload, run. In part 2, we'll dive into electronics, circuits, signals, and the fundamentals of embedded programming. Before we can control motors and read sensors, we need to understand electricity. Let's cover the essentials. Think of electricity like water in pipes. Voltage is pressure, pushing electrons through wires. Current is flow, how many electrons pass per second. Resistance is pipe narrowness, limiting flow. Ohm's law connects all 3. Voltage equals current times resistance. This is the foundation of circuit design. Electricity flows in a loop from positive through components back to negative. We call it a circuit. A breadboard lets you build circuits without soldering. Components push into holes, metal strips underneath make connections. The outer rails run the full length for power and ground. Inner rows connect 5 holes each, broken in the middle. Digital signals have 2 states, high or low, on or off, 1 or 0. For Arduino, high is 5 volts, low is 0. Pin mode sets whether a pin is input or output. Digital write sets the state. High pushes 5 volts out. Digital read checks whether a pin is high or low. Input underscore pullup enables an internal resistor. Not everything is on or off. Analog signals vary smoothly, like a dimmer switch or temperature reading. Analog read converts voltage to a number. 0 volts gives 0. 5 volts gives 1023. Arduino reads analog but can't write true analog. Instead, it fakes it with PWM, pulse width modulation. The ratio of on-time to off-time is called the duty cycle. 50% duty cycle is on half the time. Analog write takes a value from 0 to 255. 0 is off, 255 is on, 127 is 50%. Only certain pins support PWM on the UNO, they're marked with a tilde. Let's combine these concepts. A potentiometer outputs an analog voltage. We'll read it and use it to control LED brightness. Read the analog value, scale it, and write it to the LED. Turn the knob, the LED dims or brightens. Input to output, sensor to actuator. This is the pattern for all robotics. Read sensors, process data, control outputs. To recap part 2. Voltage, current, and resistance follow Ohm's law. Breadboards connect components without soldering. Digital signals are high or low. Use pin mode, digital read, digital write. Analog signals vary smoothly. Read with analog read, fake output with PWM using analog write. In part 3, we'll make things move. DC motors, motor drivers, servos, and power management. Sensing is useless without action. Motors are how robots interact with the physical world. Spinning wheels, moving arms, turning sensors. Let's understand how to make things move. A DC motor converts electrical energy into rotation. Inside, magnets and a coil of wire. Current through the coil creates a magnetic field that pushes against the permanent magnets, spinning the shaft. Reverse the polarity, swap positive and negative, and the motor spins the other way. Lower the voltage and it spins slower. Simple and effective. Here's the problem. Arduino pins can only supply about 40 milliamps. Motors need hundreds of milliamps or more. Connecting directly will damage your board. You need a driver. An H-bridge lets you control motor direction using small signals. It has 4 switches arranged in an H shape. By closing different pairs, current flows through the motor in either direction. Close top left and bottom right. Motor spins forward. Close top right and bottom left. Motor spins reverse. Close both on one side. Motor brakes. The H-bridge handles the high current. Arduino just controls which switches close. The L298N is a popular motor driver module. It can control 2 motors independently. Handles up to 2 amps per channel and includes an onboard voltage regulator. Perfect for small robots. IN1 and IN2 control motor A's direction. Set IN1 high and IN2 low for forward. Swap them for reverse. The enable pin controls speed with PWM. Let's write the code. We'll define pins, create functions for movement, and build a reusable interface. Define pin numbers as constants, easier to change later. Set all motor pins as outputs in setup. 3 functions cover all movement. Forward sets the direction pins and applies PWM for speed. Reverse swaps the direction pins. Stop sets everything low. Servo motors are different. Instead of spinning continuously, they move to a specific angle and hold it. Perfect for steering, sensor scanning, or robotic arms. Inside a servo, a DC motor, gears, a position sensor, and control circuitry. You send a signal specifying the angle and the servo moves there and holds it. No external driver needed. Arduino's servo library makes this trivial. Attach the servo to a pin, then write the angle. The library handles the signal timing automatically. A common robotics pattern: mount an ultrasonic sensor on a servo. Scan left, center, right to see which direction is clear. Turn toward the open space. This gives a simple robot spatial awareness. Motors are power hungry and electrically noisy. Running them from the same supply as your microcontroller causes problems. Voltage drops, resets, erratic behavior. Use separate power sources. Arduino runs from USB during development, or a 9-volt battery. Motors run from a pack of batteries or a LiPo battery. The critical rule: connect the grounds together. This gives them a common reference point. If your battery voltage is too high, use a voltage regulator. A buck converter efficiently steps down voltage, say, from 12 volts to 6 volts for your motors, or to 5 volts for your Arduino. Most simple robots use differential drive. Two wheels independently controlled. Spin both forward. Robot goes straight. Spin one faster. Robot curves. Spin them opposite directions. Robot pivots in place. Forward drives both motors equally. Turning slows or stops one side. Spinning runs them in opposite directions for tight rotation. With just these functions, a robot can navigate anywhere. To recap part 3, DC motors need drivers. Never connect directly to Arduino. H-bridges control direction and speed using small signals. Servos move to specific angles with the servo library. Separate motor and logic power but connect grounds. Differential drive uses two wheels for full mobility. In part 4, we'll add perception, distance sensors, line tracking sensors, and how to interpret sensor data for navigation. A robot without sensors is blind. It might move, but it can't respond to the world. Sensors give robots perception, the ability to detect obstacles, follow paths, and navigate. Let's explore the most common types. The HC-SR04 is the classic distance sensor. It sends out ultrasonic pulses, sound above human hearing, and measures how long until the echo returns. Distance equals time multiplied by speed of sound, divided by 2. 2 pins matter. Trigger and echo. Send a brief pulse on trigger. The sensor fires sound. When the echo returns, echo goes high for a duration proportional to the distance. Pulse the trigger for 10 microseconds. Pulse in measures how long echo stays high. Multiply by the speed of sound in centimeters per microsecond, divide by 2 for the round trip. You get distance in centimeters. Infrared sensors detect nearby objects using reflected light. An IR LED emits invisible light. A detector measures how much bounces back. More reflection means something is close. Some IR modules give digital output, object present or not. Others give analog, a value proportional to distance. Many have a potentiometer to adjust the detection threshold. Check the datasheet. Some sensors go low when detecting, others go HEH. The code is simple. Read the pin, react if something's there. Line tracking sensors look downward and detect contrast, typically a black line on a white surface. They use the same IR reflectance principle, but optimize for close range and high contrast. White surfaces reflect infrared light. Black surfaces absorb it. The sensor outputs high over white, low over black, or the inverse, depending on the module. Read analog values compared to a threshold. Low values mean the sensor sees the dark line. 3 sensors let you detect left, center, right position relative to the line. The logic maps sensor readings to motor commands. Center means straight, off-center means correct. All sensors off means the line is lost. This is the foundation of line-following behavior. Raw sensor data is noisy. Values jump around, sensors disagree, readings spike randomly. Good robotics code handles this. Averaging multiple readings smooths out noise. Take 10 samples, average them. The result is more stable than any single reading. An exponential moving average is even better. It weights recent readings more heavily but never forgets the history entirely. Adjust alpha to balance responsiveness versus smoothness. Real robots use multiple sensors together. An ultrasonic sensor sees far ahead. IR sensors detect close obstacles. Line trackers see the path below. Combining these gives richer perception. Priority logic. Check for immediate danger first, then normal operation, then recovery behaviors. Each sensor contributes to the decision, but the code decides what matters most in each moment. This layered approach, emergency stops override everything. Then primary task, then fallback, is called a subsumption architecture. It's robust and easy to debug. Sensors need calibration. Lighting changes, surfaces vary, components age. Hard-coded thresholds fail in new environments. Read known conditions and compute thresholds dynamically. Calibrate before each run and your robot adapts to different arenas, lighting, and surfaces. To recap part 4, ultrasonic sensors measure distance using sound echo timing. IR sensors detect nearby objects through reflection. Line trackers see contrast on the floor. Filter noisy data with averaging. Combine multiple sensors for robust perception. Calibrate for your environment. In part 5, we'll bring everything together: state machines, obstacle avoidance, line following, and building a complete autonomous robot. We've covered sensors, motors, and circuits separately. Now we integrate them into intelligent behavior. State machines, obstacle avoidance, line following, and the mindset for building systems that work. A finite state machine organizes complex behavior into discrete states. The robot is always in exactly one state. Events trigger transitions to other states. Each state has its own behavior. States might be idle, moving forward, avoiding obstacle, following line, searching for line. The robot knows what it's doing and what made it switch. An enum defines possible states. The main loop switches on the current state and calls the appropriate handler. Each handler does its work and may change the state. Each handler checks conditions and transitions when appropriate. The code stays organized. You can understand and debug one state at a time. Obstacle avoidance is the most basic autonomous behavior. See something ahead, don't hit it. Let's build a complete algorithm. Stop, back up, scan left and right using a servo-mounted sensor. Turn toward the clear direction. Resume forward motion. Simple but effective. The servo rotates the ultrasonic sensor to scan different directions. Pause after moving. Servos need time to reach position before reading. Line following uses reflectance sensors to stay on a path. 3 sensors let you detect position. On-line, drifting left, drifting right. Map sensor combinations to motor actions. Centered, straight. Slightly off, gentle correction. Far off, sharp turn. All sensors off. Enter a search state to find the line again. When the line is lost, spin in place. Most likely the robot overshot a turn. Spinning searches the area. Add a timeout so it doesn't spin forever. A competition robot needs both behaviors. Follow the line, but avoid obstacles that appear on the track. Priority matters, safety first. Check for danger before the state switch. This lets obstacle detection interrupt any behavior. Safety overrides everything. Hardware bugs are different from software bugs. The code might be correct, but a loose wire, dead battery, or backwards motor makes it fail. Check power first. A weak battery causes mysterious failures. Check connections, breadboards loosen over time. Spin each motor alone to verify direction. Print sensor values constantly during development. Print state and sensor values every loop. When something goes wrong, you can see exactly what the robot saw and what state it was in. This is invaluable. If you're building for a competition, a few principles matter. A robot that finishes reliably beats one that's fast but crashes. Simple logic you understand beats complex logic you don't. Test on surfaces and lighting similar to the competition. Know what your robot will do in every situation. If it loses the line, what happens? If batteries get low, how does it behave? No surprises. To recap Part 5. State machines organize behavior into clear, debuggable states. Obstacle avoidance scans and turns away from danger. Line following maps sensor patterns to motor corrections. Integrate by prioritizing safety. Debug systematically. Power, connections, sensors, then code. Looking back at the series, Part 1 introduced robotics and microcontrollers. Part 2 covered circuits and embedded programming. Part 3 explained motors and movement. Part 4 added sensors for perception. Part 5 integrated everything into autonomous behavior. You now understand how robots work, from electrons through actuators to intelligent behavior. The fundamentals don't change whether you're building a line follower, a drone, or an industrial arm. Go build something.